Thank you so much. Maybe sharing my screen. Can I? But I do want to say thank you, first of all, to the Ohio State University and everyone that's been in this field doing the work. I started back in 1997, actually, 1998, and I studied with Carl Pribram and Manaska Fatos. Here we go. And went to one of the first quantum mind conferences back in 2003 at Tucson, met Roger and Stewart, and it's been a wild ride. And here I'm going to talk very concisely about Alex was just talking about pedagogy, but really this is a grand experiment in my mind. This is a grand experiment that I just, and are you guys able to see the regular screen normal? All right, great. A grand experiment in social science, honestly. And you'll hopefully see that theme throughout. And I want to thank everyone for continuing to have faith and to embrace quantum as I absolutely do and love to do. So QuSTEAM is a nonprofit organization that is really just getting started. We just incorporated, and we're here to really just talk a little bit about ourselves and to see give you a little idea what we do, why we do it, and see how we can come together and who can really come to work on pushing quantum into every corner of society, to be honest. So, sorry, there we go. So we started off as an NSF Convergence Accelerator program. We won phase 1 grant. Started with 5 institutions. In phase 2, we scaled up to 20, and we reapplied with the 5. We won phase 2 award, scaled up to 20, 12 companies. We're now at 50 plus educational institutions, 40 companies. We develop modular curricular framework. We collaborate across institution types, creating a vast network, which includes employers, instructors, educators, administrators, and students. We have a strong equity and inclusion focus, including making sure community colleges and minority serving institutions, along with 4-year teaching colleges, have access to the main materials and content and resources in order to accelerate adoption of QISE material and expansion of programs. So today, like I said, we're just going to introduce QuSTEAM a little bit, provide a basic overview of what we do, a little bit of why we do it, I think, along the way, and go through some materials and examples, because this is, again, a real giant experiment. On one hand, we have a problem, and this is focused on the quantum workforce bottleneck, but this is true for STEM in general. STEM in general suffers from what I think many people can hopefully understand as preparation bias. This tight correlation between assuming a person's intelligence, their potential, their intellectual merit, and worth is directly tied to their preparation. What's the first thing anybody asks? Well, what class did you take? Have you taken these prereqs? Do you know this? Do you know this? Do you know this? Okay, now you know all of these things. I can have a conversation with you. That's a huge barrier in STEM to begin with. All fields of STEM feed into and through QISE, all the QISE feeds out into all STEM fields, including the arts and philosophy. So this workforce bottleneck and this problem of preparation bias is not quantum specific, but the solution is general. Diversity is key. We see this time and time again, study after study. So in order to build efficacy and equity, we need diversity. But in order to really have diversity, we need to be inclusive. So how do we do this? Well, it's really about changing a mindset, which is where the social science really comes into play. And this is really about stopping our current static filter process, our screening process of having a static filter and saying, here's the bars. Anyone who can pass through these bars cool, you're good enough. Anyone who just can't, whether you're too, under-resourced, too old, too whatever, too much melanin, whatever the problem seems to be, we need a dynamic process that's flexible and robust in order to assess the broader set of scientific and academic skills and principles that underlie our community's progress at large. And so we want to expand, so that's our goal right now. I'll talk about the model. We span industry, national labs, and academia, and we want to expand across the country. We are modular in focus in our curricular design and our implementation, which means that people can feed into our network materials, curricular content that they've already developed. We as a team, QuSTEAM, can work, and we'll see this later more specifically, can work to put this content together in various different ways to create a program. That program can then get pulled out into different various places like MSIs, community colleges, R1 institutions, various programs for various institutions and institution types. National labs industry also do this. We'll see here in a second that actually I'll just jump ahead. We're already getting started, and I don't have it on here, but we were a part of Sandbox AQ's industry effort to engage with New York University's Tannen School of Engineering to develop a quantum major, a BS, as well as an AI program, joint program together. And so these are varied in nature. This is a little bit of who we are, where we started, very, very diverse, not just in demographic and region, but institution type. So we currently have a lot of industry partners, and I really can't go into all of them, but you can see here at least a little bit of our industry engagements. This is really, I think, telling. This is our advisory board, our phase 2 advisory board. Now, QTools sitting in the middle, you'll see that might be a smaller company, but they are instrumental to helping us scale to under-resourced institutions and regions, as we will see, as well as QBraid. But I think the rest, for the most part, people know. So stepping back, our vision, first and foremost, like Alex was saying, no one really knows what an idea of STEM or quantum pedagogy really looks like. At the end of the day, this is brand new. All of this is brand new. And so what we want in our initiative is to create a diverse workforce by going all in at the intersection of efficacy and equity, so we can be as competitive as possible. Competition is key here. And I can go on and on and on about why diversity is essential to competition. But for me, one of the biggest and telling facts of why we need to diversify our workforce is to bring in different types of working mentalities. We're trying to change a mindset, as I had started out. So in order to change a mindset, you have to bring in people with different mindsets. And that is essential. Not only are these mindsets different, we work differently. For example, right now in the US, or rather internationally, quantum exists in a kind of startup culture. People who make $250,000, $350,000 a year at a big company, they're not looking to start their own company and have no insurance and have no real income and to make less than some of the postdocs that they're hiring. So what we have here is a similar situation to NASA, where NASA tapped first-generation college students in order to, if you will, win the space race. And that's exactly what we need to do in the quantum race. So to do this, we aim to develop and pilot undergraduate programs. We learn from what we have done, we iterate on it, and we offer continuously improving mechanisms for expanding our community to provide services and products that are varied in order to really serve all of the identified institution types. We do this through this mechanism, this process. QSTEAM is really about process. If you're going to change minds, if you're going to change a system, you need to have a process. This process is iterative. It's founded on research and development that is able to truly broaden participation and broaden the community of instructors to provide evidence-based STEM education, which is, to be honest, hopefully not too new for everyone here. So what this means, evidence-based STEM pedagogy. What does quantum pedagogy look like? Well, as a physicist, it's pretty novel, this whole idea of STEM pedagogy. But I think that outside of physics, it's a lot of sky is blue. So, and if not, great. This is part of what we're doing, is helping bring this idea of what pedagogical best practice and evidence-based best practices really look like in order to really help turn on the switch at your institution and program, organization. So we offer platforms and modules that we have designed and developed that can get pulled down and get proposed as curriculum into your curriculum committees. We also have faculty workshops, tutorials, collaborative events, as well as community with industry partners. We are rolling. We have really gotten started. American Chemical Society, we've been to NYU Tandon. We have our own summer workshops and just workshops in general, tutorials, North Carolina A&T. So as we push forward, this is the real, I think, gold that QSTEAM has to offer. And it's not just about minoritized communities. Minoritized communities, I think we were just hearing, is something very general. It's not just completely race specific, ethnicity, based or gender based. This is something that is also true for discipline. So when we talk about Kayla Lee's article in Nature Review and how we can truly diversify STEM education, QSTEAM was the only other organization that she mentioned outside of their own efforts. And that's because of what we are able to truly offer. And it's beyond what is currently being offered, which is very narrow, we'll just say, and very focused on a particular mindset and approach to thinking about and studying quantum information science engineering. And again, we hope to broaden that. This is the way we do this. We saw this picture a little bit earlier, and this is a little outdated information, apparently. But at the end of the day, we have these small bits of our quanta, if you will, modules, modular curricula. Different partners that we engage with have provided and continue to provide and develop material, curriculum. We package it into modules. Those modules then get built up into a class structure. Classes are put together into a degree program or a certificate program. At a finer scale, what we have is discipline education research being informed by industry needs, academic opportunities, national efforts, national directives that feed into the curriculum development process, which is, again, being informed by and being input from industry, academia, and national labs, government. That process gets fed into instructor professional development. Instructors not only become more aware of QISE, as today we will go through some material, but then they will also be able to, on one hand, learn some subject matter expertise, on the other hand, learn STEM pedagogy. There's a lot, like myself included, I did not really learn any STEM pedagogy going through my PhD as a theorist. We just, shut up and calculate, do what you need to do, and you'll figure out the rest later. And we have fun and our free time hanging out, talking in coffee shops, having these fun, amazing conversations. But it doesn't really belong in the classroom so far. So, is been the typical culture. So what we want is for instructors to be able to learn what STEM pedagogy is, what it's all about, why it's important, as well as help those faculty that aren't quantum experts, QISE experts, and then develop some of those skills so that they become comfortable teaching this in their classrooms. Then they go and deliver the curriculum, right? They teach, put on workshops, tutorials, all of that, curriculum delivery, output, QISE aware students. So not only do we have QISE aware faculty, we also have STEM pedagogically trained faculty, but we have QISE aware students, and we have truly students that are trained using the best evidence-based practices. So right now, what we have is stood up a prototype minor. And these are the courses that go into that minor. Course 1 is a no math introduction, and this all is designed to start at the first semester at the college level. So any community college can implement the first 4 courses here. The second set, they might not be able to, just because community colleges aren't necessarily equipped or have the infrastructure to offer upper level quantum discipline-based courses. However, the first 4 courses are all designed so that they can be taught at the community college level. And again, agreements through our collaborative network are being worked on so that community colleges can have a transfer pathway and agreement set up with a bachelor's granting institution where they can finish the rest of these courses. Now, what we have in course 1 is, what we have here is flexible. This is a prototype minor, and we have material to go with it. You'll see some of it here today. What we can do from here is work with institutions to pull down any of the modules that have been developed for these courses, and first of all, implement them in existing courses at your institution. So where I was faculty, I'm actually still currently adjunct faculty at Chicago State University, we're not able to offer new classes. It's not just about the state and curriculum committees. It's about not just bandwidth and funding. There is a absolute critical crisis with respect to enrollment. So no new courses, like period. They're just, it's a moratorium on courses. So how are minority serving institutions like Chicago State University and like so many other institutions out there going to offer this if they can't add a new course, have an instructor teach that course? Well, what we have been doing is pulling this material into, say, modern physics, into discipline-based quantum mechanics, into computer science courses, so that, and to math courses. As a matter of fact, the math methods for QISE was developed right here at The Ohio State University as a math course in the math department, and it has all the necessary components. It was not taught as a full math course in linear algebra, but it was designed as such. But again, it can be taught in any kind of way, in any kind of department, and customized to truly fit the needs of our community. So how do we do this? This really comes down to this 6-pronged approach. We front load fundamental concepts, applications, and career awareness. That in turn helps us backload the mathematical formalism, all of which minimizes the impact of preparation bias and preparation barriers. So if we start at the freshman year, first semester, introducing concepts, introducing applications, talking about what are the jobs that are not just going to be possible, that currently exist. That is motivating, right? That's how we get people to truly do the work and stick through the mathematical formalism, which is a huge barrier to inclusion. And I'll just give my own personal story. So as an example to how math is unique in its positioning to truly amplify the historical problems of inequity, I come from the south side of Chicago, southeast side of Chicago, actually. If you know where that is, then that's, you know, if you know, you know. No, people forget about the southeast side and the east side, but we're down there. And I ended up getting really lucky and got to go to school in the suburbs. So on one hand, that changed my life, changed my paths, opportunities. On the other hand, it created a huge problem for me. I was the only one of like 3 or maybe 4 students. I mean, it was 99% Caucasian, the school I went to. And in junior high, when we moved, there are tests in Illinois, students take. Those tests determine if you go on to math, algebra-based math. That then allows you in 8th grade. That then allows you to take calculus as a senior in high school. So starting in 7th grade, Illinois, we're tested and students are binned. No calculus, yes calculus. For those of us who were binned as no calculus, when I got to college and I had a full academic scholarship to Case Western Reserve University, I couldn't major in chemistry. I couldn't major in physics, couldn't major in any of the mathematically based sciences. Why? Because you need to take calculus in high school in order to really finish in 4 years. And I had 4 years. I had a full academic scholarship. So my parents, I mean, that's our life. We had 4 years. So if it didn't fit into 4 years, forget it. Now I ended up transferring, going, working, taking a little longer, transfer a couple times. But at the end of the day, I ended up finding out at age like 30 something that mathematics is truly what I should be doing. And the punchline of the story is in 7th grade, I tested into algebra. I tested in to get into calculus. But math is the unique field in which there is teacher recommendations that override test scores. So, you know, people can take it as what they want, but I wasn't seen as needing to have calculus in college, in high school, to go on to college for very obvious reasons in my neighborhood, in the community at the time. And I have a lot of stories about how all that, right? Lots of stories about minoritization. But this is just one story of somebody who is so privileged. They went to University of Chicago, went to Case Western Reserve, had full academic scholarships, and yet could not be a part of STEM community at large, right? I couldn't play in the reindeer games because I wasn't binned properly in 7th grade, even though I was binned properly. I tested into that. And then freshman year, my teacher came to me and pulled me out of class and brought my parents in, and had a conversation with us about how unfortunate it was, but I was placed in the wrong classroom for whatever reason in 7th grade. And now in freshman year in high school, I'm not getting anything wrong, and they had to change my classes, right? And so I ended up getting in honors and finished with honors pre-calc. But this is a barrier to inclusion. So in order to bring people in, we not only have to mitigate these historical inequities that still exist and are still plaguing our system, but we have to do it in a way that truly allows everyone to demonstrate their absolute talent. So one of the things I'd mentioned is this startup culture. What we have and what NASA did leveraging first generation college students is a penchant for persevering through adversity. That's something you cannot teach. That's something you cannot train. That's not something you can give to anybody. So when we are talking about front-loading concepts, applications, career awareness, we're not talking about watering down the curriculum. We're not talking about eliminating the math. We're talking about introducing things earlier so that we have more people motivated to stick through the mathematical formalism. Because like I was saying, there are so many barriers to inclusion because of the mathematics. And talking to social sciences, I'm probably hammering this home too much just because like you probably get it. You probably know what I'm talking about. But as a physicist, we're often in rooms where they're looking at me like I got three eyes, what are you talking about? This is totally fine. Everything is great. And we don't need to change anything. So this is a giant social science experiment. How do we engage people to see what they are bringing to the table at every stage of development? So when you have students come in and they didn't have calculus in high school, okay, does that mean they can't do quantum? Well, I didn't have calculus in high school. I have a PhD having worked in theory of quantum systems, right? I mean, is that an absolute no that we can't have any of these individuals? No, I don't think that's true. I think that if we focus on project-based problem solving, team building in the classroom, involving industry employers at every level of development instruction for the projects that they're doing in the classroom, for internships that they can then get afterwards, because the assessment criteria for the projects they did in the classroom were informed by the employers. So when they do a good job in the classroom on this project that the employers helped, develop and say, this is a good project, they also say, hey, this is how these students did a good job on this project and they're useful in our company. And so in order to do all of this, we really need to create formative assessment metrics, new ones. We need to come up with brand new ways of brand new ruler sticks at the end of the day. And I really hope that we all work together on this here, honestly. So what does the backwards design look like? So inverted curricular design looked like what I was just talking about, bringing motivational elements up front, pushing back the mathematical formalism. Backwards design is thinking about what it is that the students are supposed to be able to do at the end of everything. And in order to be able to do that properly, you have to know what is the evidence that you are going to accept to determine that your students, in fact, did what they needed to do. So this is our process. We start at the end and we go to the front. Then, so we figure out what do we need to know, and then how do we know that they're going to develop those skills and they have the understanding they need? What are the activities and resources that they're going to need in order to develop this knowledge and skill base? And then implement this and assess it, collect, interpret the data. How did this work? What can we do better? So as an example, a general course or curriculum learning goal might be students will use models and simulations to predict and explain phenomena that rely on quantum entanglement. Core idea, quantum entanglement. A specific learning objective aligned to assessment might be students will construct an explanation or a model for the mechanism by which teleportation can transfer information, what they will do. Now, how can they do this? Using diagrams, so construct an explanation. How can they do this? Drawing a diagram, pictures, talking about the mechanism, explaining the mechanism, how you need to communicate between sites in order to truly implement teleportation, and how that precludes faster than light communication, for example. And another way we do this is by looking at diagrammatic calculus. So diagrams and pictorial approaches have really developed over the years. And one of the crazy things I truly believe in is by taking a higher road, if you will, in mathematics and using graphical calculus, we can actually simplify the introduction of, say, linear algebra and abstract algebra. So for example, in course 3, our math methods course, we start bringing in these notions. And well, actually, even in course 1 and 2, we talk about how we have matrix multiplication, but matrix multiplication really boils down to 2 boxes acting on each other. And a matrix acting on a vector looks like a box acting on a triangle, for example. And so we want to continue to develop this along with our partnerships from QBraid that allows us to really use their platform to push as much of the formalism onto code as possible so that they're not doing pencil paper math right away, but they are able to at least get exposed to circuit diagrams, introduced to some of the notation, whether it's vector matrix notation or Dirac notation, but correlated to images, pictures, and colors. QBraid, as I mentioned, is a cloud-based platform for quantum computing that is absolutely phenomenal for educational purposes. QuSTEAM is looking to incorporate code whenever possible, particularly in Python. QBraid does this for us. Their platform is just a set of Jupyter notebooks. You are able to run quantum circuits on actual QPU devices, various ones. You see some of them there. And we allow students to work across platforms, and we allow instructors to manage your own projects. So we have our own landing page at QBraid, and we have credits that we provide to students and to instructors to run actual quantum jobs, algorithms on actual quantum computing devices. And that is truly a help because, I mean, it is truly beneficial. Being able to run the actual jobs and learning how the noise works on different platforms, different types of qubits, platforms, as well as the topology of your qubit structure. How are they connected? What's the depth of your circuit? Looking at how noise shows up in each of these situations is key and crucial. And so at the end of the day, we all coding, remote access, really important, but we need hands-on experience. So our course 4 goes through quantum labs and looks at some basic classical optics versus quantum optics in order to recognize the relationship between measurement probabilities, superposition, and interference. We want to realize stronger than classical correlations exist with quantum entanglement and how it's used. The course focuses on how the limitations of decoherence really affect real systems, as well as explore how the same quantum phenomena shows up across different experimental platforms. So you have qubits, photonic qubits, you have spin-based qubits, that are electron spin-based qubits, you have nuclear spin-based qubits, you have a whole host of different types of ion trap, right? Neutral atoms. At the same time, we are using lower cost hands-on experiments as well as remote modules for the more expensive quantum setups. This is one of the examples. So with QTools being one of our really great collaborators, we not only have experimental equipment at UChicago that Hannes, Bernine, and Danielle Cavazos works on there. They have been able to develop curriculum and test it remotely so that institutions and students at under-resourced regions are able to keep up and do remotely accessible for entanglement experiments, for example. And then we want to work with those institutions on a hub and spoke based model. We're actually submitting a proposal hopefully soon. We want to continue to bring and expand our network. I mean, that's the plan to begin with, is expanding across the country. And so we want to take this idea and really have as many places running these kinds of experiments remotely to give access to all regions and all demographics. This is a game that was revamped into VQuil, Virtual Quantum Optics Laboratory, but it's effectively the same. And you can develop photonic circuits and look at different types of game structure in that platform. But we also have, what I had mentioned, develop different types of games. This is an HOM Pong game that I've developed with actually some students of mine, former students. And at the end of the day, we see here diagrammatic calculus in a very simple form. That's where we want to go. That, and as well as that is not playing right now for some reason, but this prototype game here with the colors and the shapes is, I was mentioned before, with diagrammatic calculus. But this is where we want to go. So we see that people can use Venn diagrams without learning Cantor set theory in total, right? I mean, people take chemistry and talk about benzene and draw molecular structures without learning that these are differential operators on nodes, basically taking graph theory to a different level and using it in physics and chemistry. The same goes for below. At some point, we will be able to understand the basic elements of these lines and triangles without necessarily having to learn all the fundamental definitions of what is a group versus a set versus a category, and how do we, why can't a set of groups, why do you need category theory for all these types of things? You don't need to know all of that. So real quick, I'm going to take a quick break here and ask if anybody has any questions about the process and the model that we are working, in, and resources we are providing, or share anything that you feel would be helpful that you've done similar that has worked, or or not in your environment, in your setting. And if not, that's also perfectly fine. All right. So let's give, now I'm going to just start with, if you will, an example of what it looks like coming into a QuSTEAM workshop, classroom, tutorial. This is varied. This is again flexible and modular. So all this material can be taken apart and shared in different ways. And so let's get started. To begin with, there are 3 areas of quantum information science engineering, quantum computing being the biggest, shiniest, first seen field in the area of QISE. And that's really, I think, because there are some very clear advantages that we will acquire when we have a quantum computer the size that we need to in order to do the things that we're talking about on this screen. So one of the things that quantum computing offers is the ability to break RSA encryption. So encryption on our phones, government secrets, all of that. It also promises advancements in drug discoveries and material science through simulating quantum systems with quantum systems. But At QSTEAM, we also focus on the other areas and make sure that everything is attended to. So quantum sensing is possibly going to be the first real mover in the space. It's contentious, I know, but it's very possible. And we're seeing this work take off. Here at the University of Chicago, there's the QLCI, Quantum Leap Challenge Institute, called CUBE, Quantum Biosensing and Bioengineering. So it's a whole Quantum Leap Challenge Institute developed for that purpose. And we see that gravitational waves are at the scale all the way to organism measurements for magnetic field measurements on the scalp. We also have quantum communication. And for some reason, the slide got split up. But so quantum information, where you have the ability to communicate across vast distances in a provably secure manner, thereby safeguarding our important information like financial data, nuclear codes that we're just talking about, how quantum computers will be able to hack in the future. Well, quantum communication theory essentially has been able to establish ways and protocols that can provably secure information. So that means you can send information from one place to the next to another and know that no one eavesdropped, no one hacked that channel and listened in on that signal. Now, is this an unhackable network? That depends on how you define the word unhackable. I use provably secure. Unhackable, oftentimes people will say hacking when you talk about like a DNS error, right? Like we talk about a whole network going down, just shutting down a network. That's also hacking. People can hack a network and bring it down. Well, in a sense, nature is constantly hacking quantum communication amongst molecules and atoms through decoherence and through just noise. So we will definitely be able to hack a network in that sense if we define it as just bringing it down. Quantum networks will be in the future, in a sense, very vulnerable to that kind of hacking. But that's very different than intercepting information. That kind of hacking will be safeguarded with quantum networks, and in that sense, quantum internet, which is just a network of quantum devices and systems that share quantum information and enact quantum communication protocols. So how do we do all this? We do this with information. So in order to start at the end, that's where we will begin. What is it that we are working with and how do we work with it? Well, these are bits and qubits. And this is just to start off with some basic definitions. A classical bit is just defined as a two-outcome system. When you make a measurement, this system only has one state it can be in at a time. It can either be a 0 or it can be a 1. It's a two-outcome system in that it could be either 0 or a 1, but it's only one or the other. Qubit, on the other hand, is a two-outcome quantum system. So a two-outcome system, like we just mentioned, means that when you measure the system, the result you get is one of two possible outcomes. An example of a physical qubit is a photon, where one of the outcomes when you measure it could be in a vertical polarization state. It's oscillating in the Y direction, we'll say, or in the horizontal polarization state, in which it's oscillating in the X direction. But either way you look at it, there is a fundamental difference between how classical systems behave as being either a 0 or a 1, and how quantum systems behave. We'll talk about quantum superposition. Now, this difference between classical systems having what we call definite properties, having predeterminable properties in a sense, versus quantum systems, which, as we will see, in effect, act like they haven't really decided what property they have until they're measured. It's, not very rigorous, but at the same time, this is how they behave. This is how systems seem to behave. And this difference is really at the heart of the advantages we get in quantum information science and engineering. And so what does the superposition thing mean? What is this quantum superposition? Well, to begin with, we often hear about it in the context of a system can be in two states at the same time. We hear about Schrodinger's cat being alive and dead. Sometimes we might hear about electron spin being spin up and spin down, superposition state at the same time, or again, a photon state, which is both vertical and horizontally polarized at the same time. What does this mean? So it's often an attempt to express this quantum behavior through classical experience. And that's not always useful or productive. I take a very operational approach and just talk about the properties and consequences of this purely quantum phenomenon of superposition. But as you see, and as you've seen, and as you will see, we do use analogies along with examples which leverage games as rigorously as possible in order to get at this concept. Briefly speaking, we have three real objects, or if you will, concepts in quantum theory we primarily deal with. We have quantum systems, or otherwise quantum objects. They obey the Schrodinger equation. One has to measure a quantum system to determine what state it is. To find out what property the system has, you have to measure it, we'll just say. The quantum state, is a mathematical representation given above. And this state is associated with a set of possible measurement results. So the one I've given here, the example is of a qubit. There are two possible measurement results, 0 ket and 1 ket. Those can represent spin up and or spin down, horizontal polarization, vertical polarization. Any two outcome quantum system possible can be represented by this state vector. And when we have this system of two possible measurement outcomes, the object in question is called a qubit. So the information contained in this two-state quantum object is called a qubit. Now, how do we get at this notion? How can we think about this? We tend to think about games. Now, this is broadly speaking, and there's a lot of different efforts and people involved in QuSTEAM. So right now I'm speaking about the work that I've been doing primarily, and some of the collaborators I've worked with. But there is a lot that QuSTEAM has been doing and developing beyond this. But this should give an example, an idea of what we mean when we talk about using quantum games. So we're gonna first start with a definition. Classical systems have or objects, as we can equally call them, equivalently call them, have properties that obey this triangle of classicality. I don't know what you want to call it, but it's generally speaking, classical systems are independent of measurement. They have mutually exclusive properties. Their properties are mutually exclusive. They're always mutually exclusive. Their properties are always independent of measurement. And their properties are always a priori knowable ahead of time. So when we look at a classical object and we make a measurement on it, we can get some probability and determine the probability of having a certain result. So, for example, if we have 10 marbles in a bag, 5 of them are red, 5 of them are blue, and I pull out a marble, the chance of me getting a red marble will be 50%. Chance for me to get a blue marble is 50%. This is normal for classical objects. So what makes a quantum object different? Well, let's play this simple little game with a classical marble. Okay. And so we can try to start getting at this notion of how to use this triangle, how to think about this. So I have here in my hand 2 marbles. One's red, one's blue, and I have a box. I'll just say we have a box. And I put each marble inside. Okay. I close the bag, I shake it up, I randomize it. Don't know which marble's which. I initialize this, and I go to pull out the marble in the bag. Now, we can guess 50% chance. If I keep doing this, there'll be a 50% chance that I pull a red marble and 50% chance I pull out a blue marble. Great. So on one hand, we know that we have this marble. I picked out a red marble. Fine. We now know what color the marble was in the bag, in the box. It doesn't matter that I opened the box and I pulled out the marble. The properties of these marbles are mutually exclusive. If it's red, it's definitely not blue. If it's blue, it's definitely not red. So if I pick the red one, I know what the other one is inside. Now, this sounds humdrum, but it gets weird when we start looking at quantum marbles. So let's take another look at this. Let's take a look at the quantum marble. So now we have a quantum marble. Like I said, 2 quantum marbles. All right. And I know what it is, right? Okay. So I put in a quantum marble, the one I want. I pick it out, right? Or I have 2 and I pull one out randomly. Fine, blue. So now I have 1 marble in the bag, a qubit in the bag. I open the box from the top, and I pull it out. Okay, it's red. Well, we might have guessed that if we were thinking classically. So we put it back in the bag. All right. But I'm telling you that weird things happen when we deal with quantum marbles. So let's try it again. Pull it back out of the bag randomly, I initialize it, everything, pull it back out of the bag from the top, out of the box, open the box from the top. It's still red. Interesting. So now I put the marble in the box, initialize it, but now instead of opening the box from the top, I open the box from the horizontal angle. And now when I pull it out, there's actually a 50% chance that I pull out a blue marble. But there was only 1 quantum marble in the box. So how could this marble that was red all of a sudden become blue? Well, it turns out that working with quantum objects, like a qubit, is very much like dealing with a bag with 1 marble in it, but when you pull it out, there's still a 50-50 chances of being red and blue. Even if a red quantum marble was placed in the bag to begin with, and you know what you put it in there. So let's think about this. We see that on one hand, quantum properties are not always independent of measurement. When I rotated the object in the system, and I measured it, when I rotated my measurement device, and I opened the box from the horizontal angle, I see I get a different color. So right away, we know it's not independent of measurement on one hand. On the other hand, we also know it's not mutually exclusive. These properties are not mutually exclusive. I mean, it was red, now it's blue. So these are not always mutually exclusive. We see that sometimes they are. If you're always measuring, say in the Z basis, and you have a red marble spin up electron, you put it and you prepare it in the Z basis and you measure it in the Z basis, then great, you're going to always have that red marble. But you can choose to use a different basis to measure in. And when you do this, the properties are not mutually exclusive anymore. And therefore, they're not a priori knowable. You can't know ahead of time what color the marble is before you pull it out of the box. So this is really, really unique. This is totally different from our classical reality. So how do we think about this? Apparently, for quantum objects, the act of measurement, well, first of all, it's just not fully understood. It's called the measurement problem for a reason, right? But we do know that it seems like, especially the way in Copenhagen kind of talks about it in its interpretation, is that these systems behave as if they haven't really decided which physical property they have yet. Their properties aren't real in that way yet. They become realized when the measurement happens, when the object is pulled out of the box. Now, there's obviously a lot of subtlety here. We talk about measurement. This is something really nuanced, and it's really about, and we'll get to this, it's really about what's knowable. When we talk about quantum systems, we really talk about, in principle, this concept of classical knowability. And we'll actually talk about this here in a second. But at the end of the day, these objects just don't work the same. Quantum objects just do not behave the same as classical objects. And we will see that that's what gives us our advantages, that previously this was just a philosophical, problem that physicists had to deal with, who wanted to deal with it. It wasn't important to the rest of society because it didn't really affect anybody, can't really do anything with it. But now that we can develop technologies, computers, networks, sensors, using these quantum principles, these fundamental counterintuitive principles, that is what we are able to do here with quantum systems. And that's why it's important when people are talking about it. So let's talk a little bit about what does this idea of classical knowability mean here. So like I said, this is very subtle. How does this work? You have a system and it doesn't seem to have a physical property until it's measured. And then it kind of decides randomly which one it's going to be. That's how it behaves. So let's take a look at the hat game. There's a very traditional, almost canonical game in game theory called the hat game, or the three prisoners paradox, also equivalently called. So classically, the idea is I'm wearing a hat, a red hat, and I have two people with me we're all in the same prison, if you will, and we all have a hat on. But the hats only come in two colors, red and blue. And there's definitely both colors present. The only way to get out of prison is for us to know what color hat we are wearing, enter it into the keypad, and get out. But the problem is we cannot see what hat we're wearing. And we're not able to cheat. We're not able to look at each other's eyes and mirrors or any of that sort of stuff. We just have no access to the information about the color of the hat that's on our head. So there's three people. We're each wearing either a red or a blue hat. And definitely both red hats and blue hats are present. How do we win? How do we get out? If anybody has played this game before, great. If not, and you're not really seeing it right away, don't worry about it. I didn't see it right away either. It doesn't always translate unless you're really in person sometimes. But hopefully you can understand thinking about it. If I'm wearing I'm wearing any color hat, and I see two color of the same hat. So just say I see two colors and they're both blue. So I have my two, co-prisoners, and I see that they're both wearing blue hats. Well, what does that tell me about the hat that I'm wearing? It's very much like the marbles in the back. Once I pulled the one out, I know what the other one is. Both red hats and blue hats are present. That's like one of the only real rules of the game. So if I see two blue hats, there's only one left, one I'm wearing. And if I see two blue hats, I know that there has to be a red hat somewhere because both red hats and blue hats are being worn. And there's only one hat, that I don't know. So I must be wearing a red hat. So if I see two people wearing the same color hat, I know I'm wearing a red hat. So I go, I get out, I enter my code, red, says, yeah, I get out, cool. Now, the other two players, sorry, the little last condition is that if you're wrong, you get electrocuted or, it doesn't open. So if I get out, they know he had the right answer. He knew what color hat he had. So they say, oh, if he knows, the only way for him to know is he saw two colors of the same hat. And so they know what color they have. They got out. So those two players see me wearing a red hat. They both now know they're wearing the opposite color hat. So they put in blue into the code and they also get out. That is a fundamental, like I said, game and game theory that gets built out into more players and the rules, and you actually build out into linear algebra, matrices, vectors, statistics. So you really have all of the pedagogical elements that you need for introducing everything in quantum, everything in artificial intelligence, AI, starting in this game. Statistics, linear algebra, a little bit of abstract algebra, and game theory, right? Strategy. So looking at this, we see that we were able to do this because the hat colors are independent of measurement. They're mutually exclusive. If it wasn't red, it was definitely blue. And you're able to know ahead of time. So if I saw that two people had the same color hat, then I know what I'm wearing without even looking at it. But what happens if we do this with the quantum hat? So say that, and I'll just assume for those of you who have some quantum, math experience and you know the Hadamard basis, say that we are playing this hat game, but each hat that we're wearing, three players, three prisoners, is each in the plus state. So it's 1 over square root of 2 times 0 ket plus 1 ket. So it's equal probability of being red and blue. So now, when you play the game, we open, everyone opens their box. They go to measure another person's hat to see what color they're wearing. They're each wearing, hats, but they're in a quantum box. Can't know it until you measure it, till you open the box. So whenever we go to open the box of another player to find out what the other player is wearing, there's a random chance that is red, half red, and random half, 50% chance that it's blue. So there's no way to enforce the rule that all colors are present here. They're each statistically independent of each other. And the superposition principle does not allow for you to know what color hat you are wearing. So this is telling us that at the end of the day, quantum systems and objects seem to behave as if they exist as a set of possible measurement outcomes. You make your measurement and you find out what state, what property your system has because you observe it. This is radically different from the behavior of normal classical objects. And this is fundamentally different behavior that allows us to perform these previously considered impossible tasks, like breaking RSA encryption, like protecting information, a secret key using quantum key distribution, for example. So just to review, classical bits can only be either a 0 or a 1, whereas a quantum bit is actually possibly 0 and possibly 1 at the same time in superposition. It's as if you have 1 quantum marble in a box, and when you open it, that quantum marble randomly becomes red or blue, 0 or 1, given the statistical weight of our, alphas here. And so the probability, if it's 1/√2, then it's 1/2 and 1/2. All right, so here I am going to take another break and ask for questions, any kind of clarification. I'm going to take off my screen here for a second and see if I can see, like, is there any chats here? Okay, just making sure there was anything in chat. All right, so yes, anybody so far with any questions? Or yes, Michael, please.
Just it's a funny game with the 3 heads and the 3 people. So I wondered like the mathematical way to prepare this state, the quantum version of it would be a superposition of a kind of bell triple, like plus plus down plus plus down down plus, like all the possibilities.
That's right. So yeah. So you could prepare all of them to be in the plus state, for example, and then so in that state, just even in that simple state, you're not able to guess what color you have because everyone else is randomly.
No, but I meant, sorry, I didn't mean plus, and I meant up, up, down. So you always have 2.
Oh, yes, I see what you're saying. Yeah, the ensemble. So if you're looking at the ensemble of all the possibilities at one given time, and that's right. And so we can take this to superposition, to entanglement. Right. So that's exactly correct. So what I have here is not enough time. However, I will go through the first example of quantum entanglement in the game, but that's where I end up. It's exactly bringing back the game, looking at entangled hats, if you will, or rather the states, and then talking about, okay, what does it look like now in that setting? And what has not been developed yet, completely. It's actually in part written on my whiteboard here, and it's been there for 2.5 years, is looking at error correcting codes. So taking the game and playing error correcting codes and looking at how to determine a syndrome is present and to correct for it exactly the way you were talking about. If you have 001 and you're supposed to have a 000, then how do you correct it and how do you play the game to do that? And so this is thank you so much for that, just because like Alex was saying, we're just starting. I mean, it's really a brand new field, and no one's really, I'm not saying no one, but very few people are actually really putting the time in, myself included, to really build out examples and pedagogically sound examples that are just taking zeros and ones. So something I will say again, why do I do this with marbles and a bag, is I get to walk around to high schools and I get to bring this and I get to bring these and I hand these out and the students play themselves with it and they guess, and it's interactive on one hand. Another hand, it's less abstract. So I've done this next game many times in many contexts. And it used to just, and it is the CHSH game here. I'll bring it up here. It's the CHSH game, but it's a CHSH game, but I have taken just this marble example. And instead of using zeros and ones, I use red and blue marbles. And I map out the game with red and blue colors. So the mathematical rules are defined in terms of colors, not zeros and ones. But red equal R equals 0, B equals 1, and binary calculus, binary algebra, rules, and here you go. You have everything you need. And so what we need is more people thinking about existing examples and games and how to make them more accessible. At the same time, you'll see, we've seen a little bit of some of these games that I've been developing. Let's see. Yeah, right here, that I've been developing in order to introduce quantum to students that haven't had matrix mechanics yet, haven't had vectors, haven't been introduced to vector spaces, for example. And so this is HOM, Act Effect 2 Photon Interference, a game that demonstrates that, which also looks at entangled states. But then we have the diagrammatic calculus game here. And so we need to come up with new games. But games that are just getting at existing principles and examples that we know already. And so, yes. So again, thank you for that. That was really helpful. And I really appreciate that, because it highlights how much work we still have to do. And again, all that, these are papers waiting to be written. I just don't write them. I'm not into the publication thing, if you will. That's why I like the company aspect. I'm just trying to get these apps built so people can use them and people can develop the skills, like on the phone, on the actual Play Store. And so, yes. So with that, I will continue to move into this other example, looking at the CHSH game, a non-local quantum game. And this is actually what I use to introduce quantum, the concept of quantum, physics to high school students and to really fresh, if you will, students. I start with this, and then I go into the games that we were just playing with individual marbles, and you'll see why. So to get started, CHSH game, this really came from out of what won the Nobel Prize couple prizes back, and it's a amazing example of what's called a non-local quantum game. So what does it mean to be non-local? It means that we have these properties of quantum systems. And as Michael was just alluding to, when you have more than one system, you have a fact that these properties can get correlated between systems, between objects that have no distance dependence or space dependence at all whatsoever. So they're statistically non-local as far as their correlations are concerned. And we'll see what that kind of means here. But again, this isn't the point of the game, is to define what non-local is, but here, just to make sure I give the proper definition. And what we have is a game with really 3 boxes. All right, so I have 2. I'm the referee. I have 2 in my hand. Okay, and as a matter of fact, there's 4 boxes. There's 4 boxes.
Excuse me, we
Yes.
cannot really see. Actually, we see if you can get out of the back into the presenter mode. We see your.
Interesting. Okay. Interesting. Okay.
No, we could see you. Sorry, but your slide.
Yeah. No, I will do this again. And how was that?
No, it's good.
Okay, great. That was weird. Thank you for that. So what we have here is a game in which we have 4 bags. I have 2. I'm the referee. And as a matter of fact, Michael and Alex, if you don't mind playing this game with us right now, real fast, if you don't mind being player 1 and player 2.
I don't think I can do that.
No? Okay. All you would do is pick a color out. So I'll show you what happens. So what we do is I am the referee and I have 2 boxes. Each box has a red and a blue marble inside of it. And this is a classical game right now, this first part. So I have a red and a blue marble in each box. That's it. I'm going to randomly select one of these marbles out of the box, and I'm going to give that marble to player 1. And then I'm going to do the same with the other box, randomly pick out the other marble. It's red and blue, but randomly pick it out, give it to player 2. So here we go. So the first part of the game, I randomly select from a bag that has a red marble and a blue marble, and I give it to player 1. Okay, so now player 1 has a red marble. All right, you can write that down. Player 1 has a red marble. I have my other box. It has a red marble and a blue marble inside. I'm going to randomly select out a marble. It's also red. Okay, so player 2 has a red marble, and player 1 has a red marble. Now, we call those marbles X and Y. We label them X and Y. So player 1 had X, color X, so it was red. So player 1, X equals R. Player 2, Y was also R, because it was red. Now, the game is the 2 players answer me back with their own marble. They have their own boxes, each have their own, and they just randomly select one of their marbles, blue. Okay, so player 1, A is B, and player 2 randomly selects red. Okay, so in the chat, I'm going to put this down here actually. So what we had here was X equals red. We had Y equals red. We had A equals blue. And then we had B equals red. Sorry. B equals red. So how do we win? How can we win? How do we know who wins? There's the rules. There's the rules. So X and Y has to equal A plus B. What does it mean to multiply colors together? What does it mean to add colors together? Well, I have the rules here. Here are the rules. Red times red equals red. Red times blue equals red. Blue times red equals red. And blue times blue equals blue. Conversely, on the right-hand side, red plus red equals red. Red plus blue equals blue. Blue plus red equals blue. And blue plus blue equals red. Now, we just need to know that these are the rules. So we have here our results. We have our questions on the left-hand side, X and Y, and we have our answers on the right-hand side, A and B. So our 2 questions, X and Y, were both red. So what's red times red? Red. Cool. So the left-hand side equals red, R. Now, to figure out if we won, the answers also have to be red. A plus B has to be red. So A is blue. B was red. Blue plus red equals blue. So we do not win this time. You guys did not win. You lost on this game. But it turns out that if you decide to collaborate and talk to each other ahead of receiving the questions from the referee, you can actually win 75% of the time. Doesn't even matter what the questions are sent to players 1 and 2. If you answer wisely together and choose your answers before the questions are even sent, you can actually win 75% of the time. And that's the maximum percentage you can win. And how do we see that? Well, if, for example, if Michael and Alex were playing this game, they can say, hey, look at this, look at this. We don't need to care what happens. All we need to do is answer. We can choose our answers. The answers here are not randomly selected. We randomly selected them the first time just because we didn't know how to play the game. Now we can collaborate ahead of time, choose our answers. So if you look here, any set of questions that are asked, 3 out of 4 times, the winning condition has to be met with the answers being has to equal red. So 75% of the time, independent of the questions being asked, if you answer red and red collaboratively, you're going to win 75% of the time no matter what. Because 3 out of 4 times randomly, statistically speaking, you're going to have the winning condition. Now, that's cool. We can win 75% of the time. That's cool. But the key here is to realize that if ahead of time, player 1 and player 2 don't just share their classical strategy of communicating with each other ahead of time, but they actually share an entangled state between them. Now, they don't need to communicate. Once the game starts and the referee asks the questions, there's no more communication that can happen between player 1 and player 2. But they both have in their hands one half of an entangled state. So when the players measure their entangled state and they know which entangled state they have because they prepared it together and they know what it was ahead of time, they know what the other player has. And in fact, they can win 85% of the time, about 85% of the time, independent. And that's by doing some math. But at the end of the day, you end up with cosine squared of 4 different angles, and they come from the difference of 4 different angles. And that is going to give you your probability, and it's going to come out to 85%. So the point of all of this is to help us understand that without a quantum strategy, without this superposition of multiple objects, we cannot beat the 75% mark. We cannot win more than 70% of the time. But now that we are able to share an entangled state, we don't need to communicate, but we can now beat the referee 85% of the time. This was previously impossible. And to me, that is the quintessential example of how to think about the advantage we're looking at in quantum systems, generally speaking. It's not just about speeding things up. It's not just about protecting information. It's not just about being really sensitive to information out there and to create sensors. It's about doing things that we just couldn't before. We were just limited by the tools we were using. The tools were limiting us. And this, to me, is why, I didn't get a chance to prepare this set of talking points, but this is what I hope will bring us together, is this notion of moving beyond our current set of tools. So I think we've heard this time and time again. What is really the potential here in this quantum social science revolution is to help bring new tools, not just from physics into social science, but to bring social science into physics, bring social science into society. Actually, it's an opportunity. So for me, on one hand, I see QuSTEAM as, this bigger workforce problem as an opportunity to involve and engage people that have been historically left out. And not just, oh, boo-hoo, we want to be good people. That's just bad human being, behavior. We don't want to be bad humans. No, it's just stupid, right? Like, we don't want to be stupid humans. We want to be smart humans, and we want to be as competitive as possible. So if there's good food on the table and it's going to help me fight the war I'm going out to fight, I'm not leaving it there. I'm taking it with me. So when we have talent out on these streets, literally out on these streets, and I'm out there, we need to pull them in, because we're going to lose that competitive edge on one hand. But on the other hand, what we're hopefully going to be able to do is really be able to study the effects of social experimentation in the classroom. How do we achieve better results? Well, part of that has to be through social science and through studies and engaging with faculty across the different departments. And not to mention bringing that material into the classroom, talking about economics, talking about, again, games and game theory and leveraging these facts. Something that I haven't published, I'm not one to publish, but something that I had mentioned previously to the group is this whole notion of decision-making. I saw one of the abstracts, and it's absolutely fundamental to quantum. And I think that it shouldn't be a surprise that we see quantum-like effects in structures that are maybe not physical. Why? Because when you think about all of this and this whole game here, what we have is a set of strategies, and we have a behavior, we have an action. So as human beings, we tend to exist in a superposition state of strategies, but we can't do two things at once. We cannot implement two strategies at the same time. We have to select one. And sometimes it's random. Sometimes we pick the proper basis, and we measure in and we get the one that we want. We choose the thing we want. But at the end of the day, this notion of superposition of strategies and I'm not a collapse person, I don't like the term. It infers a physical process, and right now we don't understand this measurement process from a purely physical standpoint. However, this selection, this random stochastic outcome of the measurement, or in this case our strategy that's selected, this is very much like a quantum process. And so it should not be surprising that non-commutative elements of our decision-making process are going to lead to needing the same vector space structure and statistical analysis that we need for quantum mechanics. So yes, so let me just kind of back up here and talk a little bit about this notion of where we can come together as social scientists and physicists. And I really believe that through games and through pedagogy, there is a crosstalk that isn't just potentially fertile, it's absolutely necessary. It's absolutely essential to the growth of quantum and to the growth of QISE as a community. Again, if we want people to be doing quantum, we need to socialize this in a large sense. And so I have here some more slides that go to how do we talk about these things? So I gave some examples of what we do, how we think about it, and now I'm going to kind of talk a little bit about defining these approaches more formally. And let's see, so I have an hour left, right? So let me just see here.
Actually, you might want to leave some time for just an open-ended Q&A.
Okay, so then let me do that. So Bennett, do you want to take over from here and go through these slides, these last few slides, and then we take the Q&A?
Sure, I can run it that way. I guess since I'm new to you, I'll say I'm Bennett Brown, Executive Director of QuSTEAM, the nonprofit that was stood up as a result of the Convergence Accelerator effort headed at Ohio State to expand quantum information undergraduate education and research to diverse institutions, community colleges, and non-R1s, and to engage R1s both for subject matter expertise, a lead in instruction, and also the educational research. So the biggest effect size you can have in your classroom is to have tight alignment between the goals that you state, what you have students do in the classroom, which a second effect is active learning, how important that is, to the point where anything you do but lecture is better than lecture. So the biggest effect size is aligning goals with that learning activity, whether it's lecture or otherwise, and then how you assess the students, and to make those goals front and center in front of the students. If you do that, then you're in the treatment that gets the biggest effect size in education, really. And so I'm going to demonstrate that. Russell, you obviously have control of the slides. Go ahead. So I'm going to demonstrate that with a project that is in our course 3. Russell asked me to lead you through that, but what I'll do is I'll describe it and then take questions, and if sort of the time allows, could go into actually conducting that instruction on the basics. I'll say that this project, I gave a 30-minute and a 90-minute presentation as part of a Cal State-wide, system-wide professional development for faculty from across the Cal State institutions, and I think it's 18 of 21 of those institutions, I probably had both numbers wrong, but roughly, are Hispanic serving institutions. And so these faculty are across all different departments. And I was honored to do that just as much as this. So thank you for the opportunity for Russell and I. And I'll say that this activity is good up front because if you talk about rolling 2 dice, each of those dice can be represented by a 3-qubit register. And that really gets at the fact that well, wait a second, it's not 6, it's 8. And if I have a 4-qubit register, I can represent 16 states and therefore have roughly 32 variables and so on. So this is an 8-sided die, and 8-sided randomness is where we depart from what a lot of people are doing. A lot of people treat 1 qubit, 2 qubit, and then n qubits. And this is an example that is a little bit different. And it's also demonstrating project-based learning. So I'll describe it. Your assignment is to create an algorithm for 2 dice that appear random when they're separate. But if you have both dice, you can tell that somehow they are connected to each other, that they are correlated. That doesn't have to be quantum. They could have little machines inside that are communicating that are completely classical. But I'm proposing to you to design 2 dice that are rigged, that don't roll randomly, but they appear that they roll randomly if you only have one of them. And so typically here I would have students or professors discuss, how would you know? You have these 2 dice, how would you know that they were rigged together but not alone, which is the partial trace onto 1 die. And then to show, actually, Russell, I'm going to need the screen share just briefly. Yeah. Thanks.
Take it.
Yeah. Let's see. Am I grabbing the right one? I think. So this is the actual activity. So the goals are front and center. You should be able to describe correlations that indicate entangled states at the end of this project, and you should be able to implement an algorithm using a quantum circuit, and all your algorithms will be different. That's why this is not a straightforward learning activity. This is a student project. All the answers are different, and to see whether they're right, you'd have to delve into each student's project or automate, obviously, which is easy. And that the third goal is incidental, really. So you're going to create a fair 8-sided die first, and then you're going to create pairs. This program is visualizing the 64 possibilities where you only roll pairs, and Here's another, this is your assignment, is to create the circuit. This is like the learning activity. We all do it together, where the probability, you just have one die at first. One die always rolls a 4, and the other die always rolls a 1 or a 3 or a 5 in these proportions. And so we work through that together, and then they design one together where, say, one rolls evens, one rolls odds. So to demonstrate culturally responsive pedagogy, which is another technique that we do, and so now I'm going to pass it back to you if that's, well, I'll just keep it. I have the same slides up. Russ, where did you stop in that presentation? Let's see, you were here. Oh no, that's I'm looking at you ended here. Okay. Okay, so to run through maybe the slides that Russ didn't, other pedagogical measures are to check for understanding. So for instance, if you're representing the state of a 3-qubit register, which of these are equivalent? To use an interactive tool, which I could drop this in the chat. We could do this to understand single qubit gates and the representation of a single qubit. To use metaphors, this is a metaphor between the arrival of troops that happened on Juneteenth and quantum teleportation. To tie things to a student's culture and share those materials across a network. Various pedagogical techniques integrating the arts, but a really important one is to start with asking to draw on the student's expertise. So I'm going to open the question answer period by demonstrating that. I know you all come from campuses that are considering quantum information or have already launched programs. I know you're thinking about how to tool up in your own research or whether to tool up. What are the questions to bring in some quantum information science and engineering? And this came from, this is 30 seconds to just think about your answer, 45 seconds for one person to share, and 45 seconds for the other in pairs. So I won't implement that, but I'll ask that question for you to think about sharing in the chat. Please do. And then I'll turn it back to the organizers for a Q&A. And I can dive into that project and have everybody do it sort of together if you like.
Yes, and there's also the other game online that we can look at as well, the HOM Pong game. So anybody's, but I think that we gave them examples, that you gave examples of kind of what we have and the way we think about things and what we do and how we do it. So yeah. Any questions even on in the bigger picture about where we might be able to go together in this, what's next, what we might be able to talk about next year, honestly. I mean, you guys do this every year, right? So how can we really add and contribute to growing this event and this whole community? And
well, I have a general question. It's an incredibly ignorant question, but it's a question that maybe I should have started with at the very beginning. So it's QISE, information science, I assume is the IS. Is there any connection, or what is the connection between information science and traditional social sciences? Or is quantum information science just not relevant to political science, sociology, and so on and so forth?
That's an opinionated question. You'll get varied responses in the QuSTEAM network, I will say. You know, it's not clear to a lot of people how they might interact or where quantum exists in that space. But I see it very clearly as being an essential part of the STEM ecosystem.
So we would make the social sciences into STEM sciences then, in a sense.
Well, I mean, in a large sense, you guys already do so much of that. You know, I mean, it's social science. You know,
A lot of this.
Yeah, go for it.
Well, there's so much use of linear models in the social sciences and the quantitative social sciences, and there's evidence that in a variety of systems there are actual quantum effects, and there's no reason to think that applying quantum algorithms across the social sciences. I mean, from image recognition in brain sciences to models of ecosystems and societies. I'm really stabbing at the dark. This is your all's field of expertise, but I think it's clear that quantum models are useful, whether or not you're talking about a quantum computer, an actual quantum physical system that physicists mean by a quantum system, or what. I think linear algebra, to the extent linear algebra is useful in the social sciences, then quantum information science makes that more precise, what the capabilities are and what happens when you extend to complex matrices.
But I would say very specifically, I see like very clear applications or connections to not just game theory itself, obviously, but economics and quantum cognition. So that is where, that's where I was hinting at, or speaking to this notion of mathematical, isomorphisms or morphisms of sorts, so that you have things that are quantum mechanical and mathematical form, but they might not map to physical electrons and protons, but they might map to a system, a social system, or an organization, or an institution. And again, when you start looking at, again, this is a very personal response here, so I'm not speaking for everyone in QuSTEAM, but I genuinely believe that we start with this notion of education. What does it mean to have a quantum system? How do you think about it? And if you treat your objects like people, so like in mathematically speaking, it's not quantum related, but if I treat my math objects like people, all of a sudden I got a lot out of it, and I could do so much more with how I think about it and everything else. Zuri?
Well, I can just follow up for a second. I mean, the context of my question is that many students ask me, well, where do I go to learn this stuff? Do I go to take physics classes, for example? And the answer is, I've learned you don't go take physics classes, is my understanding. And I don't know how many categories there are. Maybe they should just go to information science. Maybe that's the answer. But are there other categories of sort of areas of work that are different, especially different or as different as physics from information science, or not, I guess?
That is the ultimate question. And I think, proposing to have new courses built out and new programs built out clearly and explicitly. We do believe that needs to happen. That's part of what we want to be doing. Look, the same problem happened with physics and chemistry. It was, how do I take this quantum stuff? Physical chemistry, you can't, that's not enough. Do you take the physics? And too much. So it's the Goldilocks problem. And it's not social science specific. This is absolutely every field of science. Mathematics has the same problem. Computer science has the same problem. And we're dealing with it within each area uniquely and independently. But yes, they do overlap.
I think for many social scientists, at least of the more qualitative and critical variety, like I am, the worry will be that human self-understandings and kind of the more interpretive, qualitative stuff that a lot of social scientists do will kind of fall out, and what we're left with will be equations. And I think that horrifies a lot of social scientists. I think even if they have physics envy or science envy, they're worried about losing the humanistic part of social science in a sense. And so, I mean, that's not something you guys necessarily grasp, but
what if the humanistic part arises out of synergy? And which it obviously does, right? When you put people together, the whole reason that we have to model it with these sort of simple, stupid equations is because it gets too complex. For every person you add, you just squared the problem. Mm-hmm. And that's wrong, what I just said, but the point is right. And it's factorial, so it gets exponentially more complex per person that you add. And There are textbooks out there, just Googling quantum methods in social science, the first course, quantum social science, looks like same author maybe. There was another one on quantum economics. You guys, some of you are published in this, and I know you're the one standing up the courses in the lead, but I just don't think that there's, I guess I'm pushing back against your first question. Like, of course, quantum matters in the social sciences.
Well, I'm
Yeah.
persuaded.
And Dr. Stimac, too, also. I was interrupting.
All right, I'll
There's a
pass
hand
it.
up.
Yeah, let's talk to Zrinka.
Cinka.
Okay. The more questions there are, or the longer the conversation, the more questions I have. I'm coming from humanities, and my questions are a little bit different. And I was wondering, you emphasize diversity very much, and I was wondering where I can find that in your program, in the modules, etc. Is it only that you imply that people coming from different cultures bring different perspectives, but you do not, at least this is how I understand it, I don't know where do you imply it in the program. And I wonder, especially because you have mentioned, Russell, you have mentioned math many times, and I was immediately having those images from India, how people used to learn mathematics there is completely different thinking. And I wonder if that is that can be relevant for that kind of another, that's not social science, but that soft approach to what you're doing. I was also wondering that there is absolutely no ethics, nothing about anything ethical, any question, this is, okay, there might be something, but I couldn't recognize that.
The quantum, I want to nod my head here to the Quantum Ethics Project at the University of Colorado, who very generously offered to disseminate their entire course on quantum ethics, and it's placed in the course 1, module D3, submodule 3. It's I can give you a pointer to that. It sounds like you've poked around in the materials.
Yes, and I would absolutely gladly like to see what kind of questions, and especially because I'm here collaborating with quantum physics, working on curriculum on STEM subjects. So I'm coming from humanities, but I'm there because of ethics and because of that kind of social science, humanities intersection of these perspectives to talk about it. And the third observation and questions. Alexander just mentioned that what is the understanding of humans and humanity, and Bennett, you just mentioned that there might be a new understanding of humanity rising from the convergence. And I wonder if there is anything you could share about that, because it is obvious that the technology is bringing a very, very new concept of humans and humanity that is absolutely contrary to that what we are used to have and deal with in humanities, and what we call humanity and education until now, universal education, etc., etc. And it is intriguing. And I would love to learn more about that, if possible. Thank you.
Yeah, I mean, from the get-go, I want to emphasize the fact that, one, we just shared some example material that comes from course 1 that we use with high school students to minimize math preparation. So when we use marbles, when we use interactive games like that, the only math that needs to be done is fractions. And so when we go through that with the students when they're doing it, so 3 out of 4 being 75%, and that's where some basic math can get introduced, like into the curriculum there. So you can use this in different ways, and you can take out the math and just go with the idea and the concept, or you can bring in any element of it that you wanted to. Another one is, I'm going to share my screen real quick here. All right. Here we go. All right. And now this game here, I can play with you all. If I can just find it. Here we go. So this is this is a Pong game, and it functions just like Pong. So you have two balls, these are photons that come out of these two photon launchers, we'll just say, and they shoot at the same angle. And these are, if these two photons arrive at the beam splitter at the same angle and speed and everything, you'll see that only two come off each side. And so this gives you an intuition of what we call quantum interference, that there are four possible outcomes here. We have two balls going into a semi-transparent thing. Half the time objects go through it, half the time objects get reflected off just like a mirror. So there's four possibilities. The two balls can go, photons can go through the mirror, and they each end up one on one side. They can both get reflected off each side of the mirror and end up with one on each side. But what we only see is when both come in, this one goes through and this one reflects and they come off together, or they both come in and this one reflects and this one goes through and they go together. We don't ever see the two on the opposite sides of the mirror. And so that's like taking two quantum quarters, putting them in one box, flipping them, shaking up, and every time you open the box, you only see heads, and tails, tails. Statistically speaking, that is absolutely impossible. And so on one hand, there are all kinds of ways to bring in quantum without equations and to get at this idea of what's impossible and help us understand a more human approach to thinking about systems and thinking about correlation. So something that just doesn't exist, but should, is the notion of studying how like a person like myself gets correlated, minoritized individuals get correlated to deficiencies. So because I looked a certain way, because I come from a certain place, my properties were correlated with being not intelligent, not having potential. And those are actually entangled in a way that, and now mathematically speaking, we don't have a rigorous equation to determine it. We might not need one, but at the end of the day, this at least helps us speak the language of complex systems. So what I will say is that on one hand, the math is not important, which is why I like diagrams. It's not about equations. I'm not about equations. What I am about is concepts. What math is about relationships. So the problem, I think, I'm just going to be very personal here again. I think STEM and general and society has a problem with thinking math equals equations, math equals numbers, math requires calculation. Not true. Math is only about relationships. And it just so happens that they have very well-defined relationships when you use certain classes of objects, like numbers that have certain properties, vectors and matrices that have certain properties. And so they're easy to use and to deal with because they're consistently defined. And it just so happens that after hundreds and hundreds of years, people have figured out, oh, well, these well-defined, consistent, rule-based systems actually map to real-world behavior and real-world phenomena. Social science sees it, physics, obviously, and the rest. So for me, math, and that's why diagrammatic calculus is so important, it's about a language. It's developing a new language to understand ourselves, the world around us, and a new tool to communicate. So now we can talk about social systems, social settings, human behavior in a way that we couldn't before, on one hand. Yes. Please.
Do you plan to make any survey with your students before and after, just to see what kind of changes there? Or you have mentioned that you ask your students to start with their expertise and to see where they're coming from and how they kind of react or learn, etc. But just to see with what kind of not attitude, but also what kind of understanding and what is changing through, what is changing in their way of thinking and what is changing in their perception of the world through dealing with the modules you're offering. Do you intend to do something like that? Is it relevant for you, or that would be relevant in social science and humanities, in educational sciences? That would be great to have.
I get the sense you're asking, like, is the QuSTEAM effort going to do that? Yeah,
but we would love to, right?
Well, I mean, QuSTEAM was a 2-year effort that started in the 2020 cohort. So, just to comment on the education research that was conducted under that grant as separate from what the nonprofit is doing, would like to do. We invite all universities, all colleges to join our effort, and don't make stipulations about what they do or don't measure, but we invite collaborations of all kinds in terms of educational research. We have a number of active proposals. I can't say that any of them propose to look at what you're suggesting, but I find it very exciting. There's a Myers 19. I'm not sure if that's Josephine Myers, but let's start something. That sounds cool.
So something that I can, as an instructor, as a minoritized person myself, and as faculty at Chicago State University, I can tell you how it has impacted my students, what I do in the classroom. So the thing about QuSTEAM is that we're an extended network, and we don't have prescribed solutions. So we don't, the one size fit all just doesn't exist, doesn't work. That's our whole thing. So we're working to customize our content and material development, delivery, assessment to do exactly the kind of what the community needs. So if this is what the community needs, yes, 100% we are with that. As an example of how this can transform lives for my students at Chicago State University, this translates to jobs. So I'm just going to get very, realistic here, very honest. Students that I work with and that I presumably, in general, teach to, these are students that they're trying to survive. These are students whose children are, like, literally, I have a student whose child was murdered on his front step a year and a half ago, like in front of his house, shot in the head while he was playing video games with his friends inside. So these are things that when we talk about how does it impact human life, the first thing that I see my communities need is opportunities and resources. And that has been absolutely transformative. And it's not just about quantum. I'm talking about my general education courses. I'm talking about the courses that are non-physics majors at Chicago State University. What it is about math. It comes down to math. Why? Because math is something that most people can relate to in a negative way oftentimes and have some negative experience with. And therefore, there's some area of math that, generally speaking, almost every individual feels like, oh, ugh, no, that's bad. I don't like that. It's terrible. I'm scared. This is awful. So when I could have students do something that they literally previously considered to be impossible, it absolutely revolutionizes their whole mentality, their whole perspective of life, what's possible, what can they do, what rooms that they go into, how they can hold their head high. Now they're like, oh, wow, if I can do this, oh, this other stuff does not seem so bad. Oh, this other stuff doesn't seem that impossible. And so for me, literally, that's my daily goal. That's my semester goal, is trying to get students to see themselves doing something that they previously thought was impossible, which, if you look back on my game, or not my game, but the CHSH game and how I emphasize it, that's the important piece to me in quantum, is that we're able now to do things that we couldn't before. And so part of that is establishing and developing new tools to understand and think about human systems and behavior and the rest of it. It's just a brand new field. And there's just been no funding in our neck of the woods to engage in that direction, but we would love to.
Excuse me, may I just interrupt you for a second? We are closing, I think, or already should close the meeting. I don't know. I just wanted to say, I understand that you empower your students I understand that you are trying to educate them to get jobs, which is absolutely relevant in life. And third thing, I think, is that what Alexander Wendt is always emphasizing when talking about we are walking wave function. You know, this is a how do we perceive ourselves. It is not only changing the material world, it is changing us from the within when we start to deal with that. And it's just important, you know, if that is skipped in the modules and program, it would be a pity, I think. It's just, but thank you very much. Thank you.
And just to emphasize the fact that when I give students these talks, I go into my background more. I just gave a little bit of the introduction to help make sure that people understand, they see. So one of the things is I'm literally the first quantum information scientist that anybody that I know of knows of from the city of Chicago, minoritized quantum information scientist. So when people in my classroom see me, I'm the only person they generally have ever seen standing in front of them doing this kind of work. So that right there is speaking to the issue. But then even more importantly, we really make sure, and I really emphasize the issues you're talking about right there, that where can we see ourselves and how do we define relations? Again, how do we think about our relationships to ourselves and with each other? And how, for me, I choose quantum because I relate to quantum systems in this way of doing things that were previously considered impossible. I am literally not supposed to be where I am doing what I'm doing. I mean, my dad grew up and I, spent most of my time, a lot of my time, 87th and Colfax, that's my daycare, that's my Wilita, that's where we live, that's where my family's from, and 103rd and Torrance. 87th Street is called Murda Avenue in Chicago. So in Chicago, when your street's called Murda Avenue, like that's saying something because Chicago is pretty serious. And so we really want to make sure, and I stress and emphasize the fact that we want these students to know where they're coming from, what they can do with beyond themselves and seeing beyond their current situation. And it's all about doing the impossible. So, I mean, I'm against all odds, you know what I mean? Like I'm here, I'm doing what I'm doing. And so when I'm in my classrooms and I'm talking to diverse students, that's the most important thing that they're seeing is that, wow, this person actually made it through all the hoops. They have their PhD and they're here right now. And that right there is transformative. And so we want to help make sure that they continue that self-understanding. It's not quantum specific. Quantum's a vehicle. So I think that that's something that I missed. For me, quantum is a vehicle. And that vehicle is, yes, a place for jobs. And you got a talk to what most people we're trying to convince a lot of people in our realm and neck of the woods that the education piece and this other piece, and we're not just watering down the curriculum and the rest of it. So next year, we can have a more directed, focused presentation to think about and explore all of these other aspects and really bring in the things that I do and highlight the social aspects of this. Because honestly, I'm used to skepticism, not the social science, but in general, like quantum, another education company, just DEI, it's the new thing, it can be very challenging so we're trying to just get our name out there, let people know what we're doing, why we're doing it, showing a little bit of what we have. But it is, for generally speaking, for the physics classrooms and early general education. But the first course is general education.
I'm going to cut in really quickly here because I have to run at 4, but Michael is still here, so he'll still be in charge. And the discussion is scheduled to go till 4:30 unless you guys are done early. But thank you so much for coming. This has been I think this is really important, and we should continue this conversation after the boot camp. There's a lot of things that I'm aware of now that I hadn't really thought about before. And I'm not going to learn the math myself ever. It's too late for me, but I think it's not too late for a lot of other people. So, so I'm going to go, but thank you very much. And Michael will take over from here. All right.
Thank you so much.
All right. See you soon. Okay.
You bet. Sorry, Matt, go ahead. And Bennett, I I had to jump in there with that one.
Oh yeah. Can you hear me?
Yes.
Thanks. Wonderful talk. I love your vision. I'm a mathematician and I struggle with teaching my grandson, and he wants to be a physicist now. But I wanted to kind of throw something out there that may or may not be helpful to you. And we can talk about this offline a little bit if you want to pursue it. But I work with quantum structures in general, and a kind of a well-kept secret is that Hilbert space and linear stuff is not the only quantum structure out there. That there's a much simpler way to describe this quantum-like world, and that is just if you think of overlapping sample spaces. So in classical probability, you have one sample space of outcomes. But what if you had multiple? So, and they overlap, but the catch is that there's
Fuzzy
no,
structures, fuzzy algebra.
well, you can do it crisp or you can do it fuzzy.
Okay.
So if I take the crisp example first, just sets of outcomes, right? But more than one.
Sure.
However, the catch is you don't have one big sample space that has all the outcomes. You have only partial experiments you can do. I can't do all the experiment, the sort of the God experiment, right? And what's beautiful about this is you can develop so many concepts without Hilbert space whatsoever, like superposition, like what a state is, what a proposition is, what a property is. And the so-called Hilbert space miracle is that the properties and the pure states and the propositions are all isomorphic. But that's only true in Hilbert space. It's not true in general. They are separate kind of concepts you can talk about independently of one another. It's a very interesting kind of approach that doesn't need matrix algebra to kind of convey. There's a famous example out there called the firefly box, where the firefly box, there's a firefly in a box, and the box is triangular shaped, and there's walls that divide each of the the walls of the box are divided in half each one. So there's, if I look straight on at the outcomes from the Y direction, I can see him on the left or on the right, or his light is not on. If I turn the box 120 degrees and look at that wall, same thing. There's a wall. He's either on the right or the left, or the light is not on. And this firefly can travel within anywhere within the box, but I can't pull the lid off. I can't do a God operation and see where the firefly is. But the firefly can go into any one of those three chambers inside this box. It's a famous example. My advisor, Dave Fowlis, and Charlie Randall, they came up with this. The Fowlis-Randall empirical logic or operational statistics kind of approach. But anyway, I just thought I'd throw it out there because it's a very simple conceptual model that kind of fits into your front loading piece, that you don't need linear algebra to talk about sets of outcomes, right? So just thought I'd throw that out there.
This is great. So you were saying Fowler.
Fowlis, I'll type it in the chat if I have access to the chat. Let's see. Fowlis, Randall. So those are the two co-authors of just maybe over 100 papers they've written together, or with other co-authors. There's this thing called the Gricci diagram in graph theory. Gricci is also somebody I've worked with, who unfortunately passed away a couple of years ago.
No, this is yes, I see exactly what you're talking about. Yes. Oh, and I know who Kerninoff is in 2007, right? Okay. Very cool. So this is exactly the kind of thing, and that's what I was trying to stress. This is so new. This area is so new. And these are, to me, this is why the math. So I was really made to believe, I really bought into the fact that I hate math, I hate numbers, I don't want any part of it, until I realized, like, oh, it's a language and it's about relationships. And so for me, math was taught as a bunch of rules that you have to follow. Yeah, that wasn't working. Now I understand it is, what are the minimum set of rules we need to get away with being able to do whatever we want to do? Like, that's how I look at it now. It's actually rule minimization, and so I like that. And I think this is exactly the kind of thing that we need to dive into and to think about and unearth. And the physics is always trying to catch up to the math, and so that is in itself its own thing. But now we're in a place where we're trying to explain the physics, so we have to catch up to the math and the physics and how to explain, and the social science and the pedagogy and all the rest of it. And so math, to me, and thinking about how to leverage these other structures and principles that we haven't really thought of, that's I think social science is going to be great for that engagement. This is great. Yeah,
that's good. That's good. So yeah, classical statistics falls out as a special case, and Hilbert space quantum mechanics falls out as a special case, where you take the sample spaces are an orthonormal basis for the Hilbert space. So if I choose one orthonormal basis, that's choosing one experiment to perform.
right.
And the set of all those sample spaces is the set of all orthonormal bases of the vector space. So it's called the frame manual, but it's a very special structure. Like I said, the Hilbert space miracle is that all those different concepts coalesce into one. So a lot of times we have a metaphysical catastrophe because if one person is talking about a pure state, maybe do they really mean they're talking about a proposition, or they're talking about a property? Those are all three different things, right? Observables
Yes.
can also be defined. And without the use of Hilbert space, you can define an observable, you can define superposition, stochastic state versus realistic state. There's the two concepts. And sometimes you could say that every realistic state is a stochastic state. And things like this could be true or false about your set of sample spaces, right? I don't want to pontificate too much, but I'd love to collaborate with you someday
Yes.
to see if we can come up with nice toy examples for students to kind of get their teeth into. I love your game approach. That's awesome.
Appreciate it. So I'm so okay. This is kind of new, but I think I have like the undergirding of what you're talking about. So is this effectively a specific example of Thomas Hardy's like toy model of the quantum, like using category theory for axiomizing?
Very related.
Yes,
that's very related.
That's what I was, okay.
So for example, if you come up with certain kind of, I guess, reasonable axioms that everybody thinks should be true, the theorem is that the only answer is Hilbert space. But many of those axioms are not. Many of those axioms are just, who says they're true in the social science world, right? Are we talking about inside a lab?
Yes.
No, that's not the social science world, right? We're talking much more complex. Somebody in the group here said much more complex. Every time you add a person, it's a factorial. It's
exponential.
I think Bennett said that.
Bennett, yep.
So, And you can see that working in this more general model very, very well, because, for example, you might say, well, geez, if I have to shut up and calculate with these non-linear things, how do I even do that? Well, you can parameterize the set of stochastic states by just looking at all the equations to set up that a stochastic state has to add up to 1 on each individual sample space.
Right.
So the sum is 1 over all the outcomes, but that's a system of equations now that you can parameterize and even maybe draw a picture of. In the classical case, it's a simplex.
Mm-hmm.
In the non-classical case, even not Hilbert case, but any non-classical case, that geometrical figure of states is a polytope, but not a simplex.
So oh man, listen. So first of all, there's a reason why I harp on category theory, and I'm a crazy person. I'm trying to sneak it in, but to everybody else in my field. But the reality is, I really believe that exactly what you're talking about. We need to explore fundamental structures and this new language. And for example, that's part of my dissertation research, is looking at complete positive maps and where they fail in open systems. And so exactly what you're talking about when you're talking about stochastic, yeah. And so it turns out that you can only have a dynamical map well defined if you assume that your initial states are in tensor product form to begin with. And so what happens if you don't have that situation? And so this is, and different people have taken different approaches. So they've used the stochastic calculus approach, but there's others, and I genuinely believe that category theory is going to help us get at and think about these structures deeper.
Yes. Oh, that's
100%.
great.
100%.
And then now if you talk CRISP, the CRISP case, like we were talking about, is each outcome is multiplicity 1, but eigenvalues can have multiplicities, right?
That's right. Degenerate. Right.
Even in Hilbert space, you have that, right?
Right.
And in number theory, you have the multiplicities of the prime factorization of any integer, right? You have multiplicities like 2 squared times 3 to the first, right? So simple cases,
whenever
you have multiplicity.
Norms, you have all kinds of multiplicity, right?
And
of course.
But in the CRISP case, these structures can be thought of as manifolds of Boolean, like the locally Boolean, right? But in the case where there's multiplicity, where you have multisets that are overlapping instead of just plain old sets. So you have a multiset system, which is a set of multisets. Then you could still talk about blocks, but the blocks are not Boolean. They're almost Boolean. They're pseudo-Boolean. They're something called an MV algebra. M like Mike, V like Victor. MV algebra, which comes from Chang's, Lobachevsky's, infinitary logic type stuff. But if it's locally classical, that's exactly what we're kind of getting at here, is one observable is classical when you just consider the one observable. But you can't simultaneously measure 2 non-compatible or non-commutative observables in the same experiment, right? So those are independent.
This is amazing. So Michael, I'm gonna get you right now. Just 2 things real quick. So on one hand, I'm a big fan. I know actually Griffiths, he is huge, he started the consistent histories approach, right, Bob? And this speaks exactly to his language. And then polytopes, gosh, we got to talk about that, because open systems and looking at multiplicities and all that, that was what I was looking at post dissertation. Michael, real quick, I mean, I know we only have 10 minutes. Apologies.
Yeah, sorry,
sorry, Matt. I'm just gonna, and then we can maybe come back. But oh goodness, I will jump off and just live. This is where I live and wanna, like we definitely need it. Please email me. I'm just sorry, Mike. I'm gonna put this in the chat.
Thanks for sharing. This is great stuff.
Yes, thank you, Michael. Please.
Yeah, so we have 10 minutes left. So first, thanks for providing this extended overview. So it's much clearer to me now what QuSTEAM is about, and it was interesting that you had time to show us all the facets. So I wanted to bring the discussion, the remaining minutes, back to the social aspect, and especially in the way you presented it in a personal note. So. And what struck me is, and what was struck me actually when I came to America, growing up in Europe, how people put themselves into boxes and then they keep themselves here, and like it's a mental box. I mean, and when you grow up here, I think you are used to this and people do this, so you start doing it. And when you come from outside, it's like shocking. And I saw this first when I had to put in where do I fit in the moment
Literally check your box.
and to increase diversity, or it's like, and back then I was not even doing quantum related to social science. I thought, what is this doing? It's is actually generating the opposite of what it's intended to, because it's getting people used to think in boxes. So, and I think this element, especially for your students who have now the understanding or the mathematical apparatus of quantum mechanics, given the overall project, I think to get this idea in, that it starts here, minorities and so starts here, regardless of where you are, inside of the category or outside. And because this is, I think, a powerful message which quantum mechanics can tell us.
Well,
put yourself in a box and bring this message out.
I guess I want to comment on a few things you said, because QSTEAM is so intertwined with the effort to do justice to our history and correct wrongs by making sure that there are on-ramps for everybody in the future quantum economy. So, you know, it is those boxes still apply because reparations were never paid, and there are people who have inherited from their very parents ineligibility for the GI Bill because of those boxes. So you can't just get rid of them and pretend that it's so. Okay, politics aside, you know, that starts to get into that swampy territory quickly. I do want to say, in answer to the earlier question about like, well, where are those materials? It's not our effort to diversify the future quantum workforce is not just in the materials. It's true. I showed, for instance, some materials that came out of a majority Lakota classroom. And in general, good pedagogical measures like stating goals front and center and asking students to base the entry into the material in a social way to build community and so on. Those are efforts that narrow gaps, that broaden participation. But we also, in who we aim to scale to faculty who are at non-R1 institutions and are overrepresented in our community in terms of underrepresented folks in academia. And so, you know, overcoming those barriers takes a lot of different strategies, and some of them do require thinking about those boxes, I think. But in terms of like, does quantum mechanics help people break out of those boxes? I love that, Michael. You know, we are a superposition of our identities. Identity politics is nothing but superposition. And I think maybe that gets at, I'm going to bring it home here and take less than 60 seconds. How can quantum be used in social sciences? If a person, you know, if you're doing agent-based modeling and you've got a community of 10,000 people and each person is an object, a data object that represents their experiences and assets and, you know, and connections. Well, those connections, as I pointed out, scale exponentially, but really that's a very simple algorithm in quantum programming, because you just take a person who is a superposition of all these attributes that could be a superposition of all the people, and you apply this I'm going to say things wrong, and Russell's probably like, no, just stop, man. But in 60 seconds, you can apply an algorithm so that all the people who think, say, no, get rid of the boxes and the people who have political power and the people who this, that, and the other thing. And that algorithm just got applied to every pairing, or if you wish, every triad of people in the society sort of at once. That's the quantum parallelism that is oft misunderstood. So as you model a bigger and bigger system, interactions that are 2Ys and 3Ys get out of control on a classical computer, and they don't on a quantum computer. That's precisely the kind of problem that a quantum computer could be good at. And so I really appreciate being involved in something that's going to implement one of QuSTEAM's central ideas, which is that it's all disciplines, break down the silos. It needs to converge, engage all people across all interests. And I said in the chat, like Carnegie Mellon, arts is absolutely, there is an answer to that. From the QuSTEAM perspective, the social sciences belong in the conversation. So again, thanks.